this example, it's a multi-part example, we're going to look at how conservation of energy can apply to electric potential energy and voltage. So here is the example. There are two walls in a region of space. So the idea here is that, pretend straight lines. We have two walls. One wall is at 0 volts. The other one is at 10 volts. At the midpoint between them, so here roughly is the midpoint, this is the 5 volt mark in between 0 and 10, we have a proton and electron sitting and waiting for us to do things with them. So there is our electron, here is our proton. I seem to have lost my minus sign. Now, many questions here. We want to compare the motions of the two charges, including comments on their directions of motion and their changes in electric potential energy, kinetic energy, and velocity. We also want to answer the question of which particle reaches the wall first. So, lots of parts here, 6 if you count them all. Okay? So the first question, what direction do they move? If you think about the electric potential due to a point charge, that goes as kq over r. So the potential due to a positive charge will be a positive number. The potential due to a negative charge will be a negative number. Therefore, the higher voltage region is where the electron is going to want to move, because it is moving towards where positive charges would be. The proton is going to want to move away from the positive charges and toward the negative, therefore it's going to want to move to the 0 volt wall. So compare their directions of motions. The motions are opposite directions. Okay. Compare their changes in electric potential. Well, the change in electric potential for the proton will be its final potential minus its initial potential, which is 0 volts minus 5 volts, or negative 5 volts. The change in potential for the electron will be its final voltage minus initial voltage, which is 10 volts minus 5 volts, or positive 5 volts. Okay, so far we have that they go in opposite directions, and their potentials change by the same amount, but with opposite signs. The proton moves to higher potential, which means the proton moves to lower potential, which means it loses electric potential. The electron moves to higher potential, so it gains. Okay, so now let's look at the change in electric potential energy of these two. Begin by saying that the change in electric potential energy will be the charge multiplied by the change in potential. Remember, the charge of a proton has a value of 1.6 times 10 to the minus 19 coulombs, and the charge of the electron is the same number, but it's negative. Okay. So the change in electric potential energy for the proton will be the charge of the proton times the change in the potential of the proton, which is 1.6 times 10 to the minus 19 coulombs, multiplied by, for the proton it was a negative 5 volts, and when you put that into a calculator, you get negative 8 times 10 to the minus 19 joules. And that negative means that it has lost electric potential energy. But we would expect it to lose electric potential energy. If you think about a ball falling, it starts at high gravitational potential and ends at low gravitational potential. So it loses gravitational potential energy as it falls. For electric potential energy, the change in electric potential energy for the electron will be the charge of the electron times the potential of the electron, which are the exact same numbers, but the minus signs move around. The charge of the electron is negative, but its change in potential was positive. Therefore, it gets the same change in electric potential energy. Now let's consider the change in kinetic energy. By conservation of energy, we know that the initial energy has to equal the final energy for a system. We have two possible energies we're playing with. We have electric potential and kinetic. So each of these equals the sum of electric potential and kinetic. And now I want to rearrange this. I'm going to move all of the KE stuff to the right and all of the electric potential stuff to the left. And that gives us that the change in electric potential energy with a negative sign, because I'm bringing this over. Let me back up a step and just fill in the blanks really quick for you. Erase, erase, erase. Okay, so now bringing all the electric potential energy stuff this way. Right. So the initial electric potential minus the final electric potential energy equals the final kinetic energy minus the initial kinetic energy, which tells me that negative change in electric potential equals the change in kinetic, which means the change in kinetic energy for the proton will be a positive 8 times 10 to the minus 19 joules, and the change in kinetic energy of the electron is the exact same number, and in this case it is positive because you are gaining kinetic energy as you lose electric potential energy. The next question is, which one's moving the fastest once it hits its wall, or right before it hits its wall? For that, we have to use the fact that kinetic energy is 1/2 mv squared. So change in kinetic energy, remember, is KE final minus KE initial. We're told it's released from rest, so the initial KE goes to 0. Right, and KE final is 1/2 mv squared. You can solve for V final. So V final squared equals 2 times KE final divided by the mass, which means that V final is the square root of that. So the mass of the proton is 1.6 times 10 to the minus 27 kilograms, which means when you plug everything in, V final is the square root of 2 times 8 times 10 to the minus 19, yes, joules divided by 1.6 times 10 to the minus 27. So for the proton, that works out to be 31,622.8 meters per second. The mass of the electron is 9.1 times 10 to the minus 31 kilograms. So V final, when you plug everything in, turns out to be 1,325,987.1 meters per second. So they both have the same kinetic energy, but because the proton is much more massive than the electron, it is moving much more slowly when it hits the wall. Because the electron is moving so much more quickly, it reaches the wall first, which is the answer to the last question.